I'm Ken Campbell, and here in my shed with all this paraphernalia, I'm going to recreate the experiments which changed the world.
An eclipse, like this one, transformed our understanding of space, time, and the universe. In 1919, a British astronomer went to test a theory that was one of the biggest ideas of all time, the general theory of relativity. I'm going to relive that experiment and find out why it turned our world upside down. That theory was the brainchild of Albert Einstein, the first scientific superstar. Einstein was born in Ulm, Germany in 1879. He was a plodding, introverted child. His parents thought he was rather stupid. However, he showed tremendous determination and patience. He built houses of cards 14 stories high. "It's not that I'm smart," he said, "it's just that I stay with problems longer." Einstein had a curiosity about the world that lasted a lifetime. When he was 5 years old, little Einstein got very ill, and his dad bought him a magnetic compass, thought it'd cheer him up. And little Einstein really perked up when he found this. He found that no matter how much you twist it and turn it, whatever you do with the thing, that needle always points north. This was his introduction to science. Einstein became obsessed with the latest theories in physics.
You're travelling along below the speed of light and you've got your mirror's travelling along.
At the university in Switzerland, he was bored by the outdated curriculum.
So Einstein would cut classes and, in the meantime, be engaged in vivid discussions in philosophy and physics, talking long into the night upon topics that were hardly dealt with in his curriculum.
By now, he'd blossomed into the life and soul of Zurich Cafe Society and fell in love with fellow physics student Mileva, whom he later married. But his studies suffered. He left university with a mediocre academic record and few prospects. After months of job hunting, he was eventually hired as a clerk at the Swiss Patent Office. Einstein's job was to evaluate new inventions. This low-grade post suited him perfectly. It gave him plenty of time to ponder the riddles of the universe.
We know that Einstein kept his own work underneath the official papers of the Patent Office, and when times were slow in the Patent Office, he would simply turn to his own work and pick up his calculations or his line of thought.
He was preoccupied with the big puzzle of 19th century physics, which was the very peculiar way light behaved. Very peculiar indeed. First, we have to understand relative motion. Relative to an observer on the ground, I'm travelling at 50 miles per hour. Relative to the driver of another car going at 30, I'm only going at 20. Much to everyone's horror, light doesn't behave like the car. Two scientists, Albert Michelson and Edward Morley, did an experiment in 1887 which showed that the speed of light does not change even if you are moving relative to it. Here's my version of their experiment. This is my famous patented light speed measuring device. It measures the speed of light and the speed of the car. Right, my assistant over there is going to flash his light at me and we're going to measure its speed. You ready, Dan?
Ready.
Dan, flash it at me. As expected, my machine has measured the speed of light to be 186,000 miles per second. So what happens if I drive away from my assistant and his flash? Now I'm driving away from the light.
So I would expect my light measuring equipment to show that the light is travelling at a speed of 186,000 miles per second minus the speed I'm travelling at, okay? So let's see what happens.
Now let's imagine my car's top speed is 10,000 miles per second. My meter should read light speed to be 176,000 miles per second.
Go on, flush again, Dad! Wow, man, the speed of the light still stays the same.
The fact that the speed of light never changes no matter where you are or how fast you're moving seemed a contradiction. It mystified every physicist, including Einstein. Einstein went back to basics and asked himself, what exactly is speed? It's distance divided by time. The speed at which I'm walking is the distance between these two trees divided by the time it takes to do it. Einstein pondered how this definition could explain the fact that the speed of light is always constant. One day, Einstein was walking in a park with his friend Besso, when suddenly...
I got it.
The answer was brilliant and challenges our fundamental laws of the universe. Einstein realized if the speed of light has to stay constant, time has to slow down or speed up. And distance has to shrink or expand. This was the cornerstone of his special theory of relativity. This startling new theory had taken over his life. His wife, Mileva, resented his obsession with physics, as he now spent precious little time with her and their two children. Their marriage began to crumble.
After their initial real closeness when they were students, Mileva and Einstein had gradually separated, and Einstein became involved with his cousin, a widow, Elsa. He had several affairs. Elsa would politely leave the house and spend the day away when she knew that Einstein was meeting his flame, and not ask any questions, not push that particular boundary.
Despite his turbulent home life, Einstein knew his work wasn't finished. Although special theory was revolutionary, it still didn't explain a fundamental force of nature: gravity. Einstein pondered again the bizarre behavior of light. I'm going to do my version of one of his famous thought experiments. Let's say my shed is moving through empty space at a constant speed. In other words, my acceleration is 0. I would, of course, be weightless. I'm now going to turn on the shed's rockets. As the shed accelerates upwards faster and faster, it feels like there's a force pulling me to the floor.
The shed's rockets are now accelerating me at 9.8 meters per second. This is actually quite comfortable. Now moving up to 50 meters per second. I can feel myself being dragged down. And now moving upwards now to 100 meters per second, and 500 meters per second. Go for it, 1,000 meters per second. Ah! I feel like jam.
Einstein now asked, what happens to a beam of light that shines across my accelerating shed? It takes time for the light to travel from one side of the shed to the other. But because I'm accelerating, by the time the light's travelled across the shed's moved upwards. So, from my point of view, it looks as if the light beam is curving downwards.
But that can't possibly be, thought Einstein. Light always travels at a constant speed and in a straight line. It doesn't bend. And then he came up with an incredible answer to this paradox. No, it's not the light, really, that's bending. It's the space through which it's travelling. That's what has bent. Listen, this is such an extraordinary idea. I'm going to repeat it. If you're accelerating, then the emptiness, the void itself, space, is curved.
So what's all this got to do with gravity? Hang on, just let me slow my shed down before it falls apart. Einstein realised that accelerating through space isn't the only situation in which you feel pulled to the floor. Gravity glues your feet to the ground in exactly the same way. In fact, now I've reduced my acceleration to a more comfortable 9.8 meters per second, it feels exactly as if the shed's sitting in my garden on Earth. So being in an accelerating space shed is the same as being pulled by gravity. Einstein called this the principle of equivalence. Einstein put the two ideas together and came up with an extraordinary conclusion. Acceleration bends space, gravity and acceleration are equivalent, therefore gravity bends space. And this is Einstein's general theory of relativity. When it was published in 1916, the handful of people who understood it were amazed. But so far, it was just a theory. Einstein wanted proof, and for that he needed a total eclipse of the sun.
Lord, won't you
Theory of relativity says gravity is curved space. To show me how curved space affects light, Peter Coles, an astrophysicist, has brought along a trampoline. This two-dimensional grid represents the universe defined by Isaac Newton, where time and distance are always regular. When Einstein came along, he messed it all up.
So we now have the sun in place. You see, the sun's a very massive body, so it exerts a very strong gravitational effect on space and time.
Yeah.
And you see that represented here by the way the grid is now deformed. It's curved, especially near the sun. And one of the consequences of that is that light rays, which in the absence of the sun were straight lines, are no longer straight lines. And you can see that if you actually try to send a light signal past the sun with your golf ball there. Great.
So if Einstein's right, light from a star follows the curve in space-time when it passes close to the sun on its way to the Earth. But because we assume light travels in a straight line, from our point of view on Earth, the star looks to be further away from the sun in position B. If he's wrong and gravity doesn't bend light, the star will stay in position A even when the sun is there. Of course, normally you can't see a star near the sun because it's too bright. But there is one time when you can see the star, during a total eclipse of the sun. Einstein predicted the shift of the star with the complex maths of general relativity. What he needed next was someone to take a photograph of it during an eclipse. That man was Arthur Eddington, a respected British astronomer. He was entranced by Einstein's theory and was desperate to prove him right. So in May 1919, he put together a team and set sail for the African island of Principe. I've come to Alderney in the Channel Islands for a prime view of an eclipse so that I can repeat this historic experiment. This tiny island is stuffed full of enthusiasts, TV crews, professional astronomers, bulging with the latest gadgets. They're here to capture one of the most magical moments of nature, a total eclipse of the sun lasting 1 minute 40 seconds. My state-of-the-art telescope is this. Well, it was in 1919. It's a smaller version of the kind Eddington used, and it belongs to veteran eclipse chaser Michael Maunder, who is showing me how to take a photo using something called the Mexican hat trick.
In order to get an accurate time of about 1 second, the easy way is to say 1,000. And when it's all ready to make the exposure, 1,000. Simple as that.
Yeah, very good.
It's roughly an hour to go now before the eclipse. Big black clouds now. Occasionally we see a little glimpse of the sun. It's like everything is kind of funneled down to just this one little moment, well, I don't know, 1 minute, 40 seconds that the Lord might give us to get as many shots as possible.
There's not much hope of seeing any stars through all this cloud. But the weather was even worse 80 years ago.
The major problem that they had in Principe was almost catastrophic. On the morning of the eclipse, it was completely overcast. There was a torrential thunderstorm, and it looked like they weren't going to be able to get any data at all.
Back in Berlin, Einstein was waiting with bated breath.
And it's 4 minutes, something like that, to go. Okay, I'm all ready here.
The eclipse in Principe actually happened in the early afternoon, and by that time the thunderstorm had gone and the clouds were starting to break up.
It's getting very dark now. Just must be a few seconds now away from totality. Right, okay, let's take it. First one, removing the plate. Oh, 1,000. Plate out. Second exposure. 1,000.
Well, I managed to take 2 photographic plates. Eddington didn't do much better.
Out of all the plates that they took, there were only 5 that were usable, and because of the high cloud, many of the stars which they would have been able to see in better conditions were not visible, so most of the plates only had 2 or 3 stars with measurable positions on them.
Back in Cambridge, Eddington's next step was to compare his eclipse photographs with a reference plate. This plate was taken of the same star a few months earlier, when its light would not have been affected by the sun's gravity.
See, it's actually very small.
He then carefully compared the star's position on the 2 plates.
This is enlarged.
This is enlarged about 50 to 100 times on this screen here, so we can see quite a big image of the star. So we're placing one of the plates that Eddington took before the eclipse with the star field on it, and we're going to very carefully center the star under the cross wires here. And now we can take this plate out and replace it with the plate that Eddington took during the eclipse. And of course, if Einstein is right, the star will no longer be on the cross wires. And if we do this very carefully, you can see that, in fact, the star is not on the crosswires.
And that tiny movement made all the difference?
It certainly did.
The scientific community eagerly awaited Eddington's results. November the 6th, 1919, a joint meeting of the Royal Astronomical Society, the Royal Society of London. Atmosphere here described as being that of a Greek drama. Were folk here's very fundamental views going to be altered tonight? What were the results of Eddington's experiments? A deflection of light takes place of the amount demanded by Einstein's generalized theory of relativity. Excitement, pandemonium. Ludwig Silberstein jumps to his feet, points to the portrait of Sir Isaac Newton, says, "Gentlemen, we owe it to that great man to proceed very carefully before we start retouching or modifying his law of gravitation." Sir Oliver Lodge walks out, and then Chairman J.J. Thomson says he is confident that the Einstein theory must now be reckoned with, and that our conceptions of the fabric of the universe must be fundamentally altered. Crowd swayed, Einstein, hero. Overnight, Einstein became a superstar. The war had just ended, and the public, tired of endless stories of misery and devastation, embraced this archetypal image of a gentle, absent-minded professor. Thousands of articles struggled to explain his theory. Housewives were now discussing time dilation and space travel. Relativity was the new buzzword. Einstein was propelled to the status of a Hollywood icon.
Einstein became a sensation. Charlie Chaplin actually put it well. Charlie Chaplin described the fact that people cheered him because everybody understood him, and they cheered Einstein because nobody understood him.
The general theory of relativity overturned our traditional view of space and time and helped us understand such cosmic phenomena as black holes and the Big Bang. Einstein single-handedly created the first new model of the universe since Sir Isaac Newton over 250 years earlier.
Einstein took the principle of relativity and said, well, if this is right, then these are the consequences. We have to abandon these pictures. And he had the courage, the intellectual courage and the imagination to follow through to the consequences of those. And for me, it's one of the great intellectual achievements ever.
The groundbreaking discovery of radium and